Alright, so let's look at this problem. The rod shown moves to the right essentially in zero resistance rails at a speed of 3 meters per second. If B is 0.75 Tesla everywhere in the region, what is the current through the 5 ohm resistance? Okay, so now here's the thing. Then when the rod is moving to the right, the EMF induced in this section is what comes into play, because that's what drives the current. That's where it's connected. So, and the length of the rod would be 4 centimeters. Okay, so the EMF induced in the rod is BLV, and B as you can see is coming out of the sheet of the paper. And let's calculate the EMF. It's so 0.75 Tesla. That's a strong magnetic field. 4 centimeters, which is 4 times 10 to the minus 2 meters, and the velocity is 3 meters per second. Okay, so the induced EMF is 12 times 9, so 9 into 10 minus 2 volts, okay, or 90 millivolts. So that's the induced EMF. Okay, now Lenz's law tells us the direction of the current. So let's see, as this thing moves to the right, the flux through this coil is increasing, since the flux is coming out of the plane of the paper. I mean, the B is coming out of the plane of the paper, and as it moves right, the flux is increasing in this direction, in the direction coming out of the plane of the paper. So the induced current should be such that it wants to oppose that, and it needs to, the induced field needs to be into the sheet of the paper. So induced to fight that, and that can be done by producing a current, inducing a current in that direction. Okay, so does the current circulate clockwise or counterclockwise? It circulates clockwise. Okay, so that takes care of what is the current. Okay, so the current is induced EMF divided by resistance, 90 millivolts, divided by through the 5 ohm resistor, and that's 18 milliamps. So the induced current is clockwise and it's 18 milliamps. Okay, that takes care of this problem.